Alrighty, going to give you a quick overview of radiation, the nucleus, and nuclear reactions. And let's start off talking about the structure of the atom and the nucleus. Thinking about the atom, protons and neutrons make up the nucleus of the atom. And in general, these are called nucleons. So anything that lives in the nucleus is the nucleon. And each one of these particles is much, much larger than each of the electrons that are orbiting the nucleus. And when you're talking about what the element does chemically, you're looking at the number of protons in the element. That's going to tell you what it's capable of doing, and it's going to kind of drive the structure. The neutrons help hold the nucleus together by spacing out those protons. And in a neutral atom, the number of protons is equal to the number of electrons. We're going to talk a little bit about the strong nuclear force, which is what holds that nucleus together. It is a whole lot greater than the electrical force between the nucleons. And as the little particles move farther and farther away from each other, that strong nuclear force gets smaller and smaller at a fast rate. So overall, the larger the nucleus is, the less stable it is. And if we kind of compare the electrical force to the nuclear force, so think back to what you know about the electrical force, you got to wonder how come there's two protons in there with a positive charge that can be so close to each other. And the reason is that nuclear force, that's kind of the glue, is just much larger until they get far enough apart that it's not. So if you look at the drawing here, protons A and B are close enough that that nuclear force holds them together. It's greater than the electrical force. But if you're looking at the distance between A and C, at some point that's going to get large enough where it's not going to be enough to hold that nucleus together, and that's where you start getting radioactive decay. And when you're talking about radioactive decay, we're going to kind of dig a little bit backwards and think about Einstein's mass energy equivalence. And we're going to talk about mass becoming energy. And the radioactive decay occurs when the nucleons are pushed apart by repulsion. So when those nuclei get so large that the nuclear force can't hold them together again, they start to come apart, spontaneously decay. When it does this, the neutron emits an electron and becomes a proton. It doesn't want to be a neutron all by itself. And then if you look at the masses of a proton and an electron, it's less than the mass of the neutron. So some of that mass turned into energy. We know it didn't just disappear, so it's going to become some energy. So there are three types of radioactive decay. You have alpha decay, which is a low energy particle. It's going to be a helium nucleus with 2 protons and 2 neutrons, and it's positively charged. It's an actual particle, and it can be stopped by paper or skin. Beta decay, when the neutron ejects an electron and that neutron becomes a proton, you get that energy that's left over. It ends up being negatively charged, that negatively charged electron with some energy, and it can be stopped by things like clothing or wood. Once again, doesn't travel very far. Near gamma radiation, and that's that high energy electromagnetic wave, and it's caused when electrons drop from one energy level to another, and it's an electrically neutral, massless energy because it is an electromagnetic wave. And when these decays happen, you end up with isotopes. And isotopes is when the neutrons are different than the number of neutrons found in just the base stable atom. It doesn't change the element chemically, but it could be that the isotope is radioactive. It's not all the time, but some of the times it can be. And so we have an example here with 3 different hydrogens. They're all isotopes. They're all still hydrogen. So adding neutrons changes the mass, but not the atomic number. So you have hydrogen, deuterium, and tritium. Tritium is the one that's the most unstable, and it's going to undergo beta decay. And just kind of quick review looking at the symbols for the elements. That top number is the atomic mass number, and it tells you the total number of protons and neutrons in the nucleus. Then the bottom number is the atomic number, and it's just the number of protons. And since we're talking about decay, we have to talk a little bit about half-life. And the half-life of radioactive material is the time it's needed for half of it to decay. And you can't really tell which atoms are going to decay specifically, but you know how long it's going to take for half of it to decay and change into something else. After one half-life, you have half of the material. After two half-lives, you have half of that half, so you end up with a quarter of the material, and it just goes on like that. We've got a simplified equation in this course. We've got the fraction of the total material remaining is equal to 1/2 raised to the power of the elapsed time divided by the half-life. N over N naught. N is the ending amount, and N naught is what you started with. So that's a fraction of material. The little t is the elapsed time, how much time has gone by, and capital T with the 1/2 notation is going to be the half-life. And the half-life for the elements are known. So it's kind of a constant. And this decay is the way it's got this power set up. It is an exponential decay. All right, so here's an example of a half-life calculation. We have a waste product of a nuclear power plant is cesium-137, and it has a half-life of 30 years. And the question is how much of the original cesium-137 would remain after 120 years. And so in this instance, we're looking for that fraction of N over N naught. And we have the amount of time, which is 120, and we have the half-life, which is 30. And so when you plug everything in, you have 1/2 to the 4th power. And if you do the work for that, you end up with 1 over 16. And you might need to use the decimals on the homework for this kind of a problem. Remember that you're putting the numerator and the denominator to the 4th power, each one. So just a quick example to walk you through it. And then the little last bit is the types of reactions. It's good to know what the types of reactions are. Fission and fusion, you've probably heard those words. People are trying to make fusion work because that would provide a whole lot of energy. They both do result in a large amount of energy, but if you look at the comparison, you'll see that fusion is what's happening on the sun, and fission is what's happening in the power plant. So the fusion is a little bit harder to control. Atoms are fused together, so you end up with the two hydrogens fusing into one helium. The waste product is safe, so the waste product is going to be helium. And it takes a really, really high temperatures, like the sun, to make these reactions happen. So not very practical with our understanding right now. Nuclear fission is what's going on in the power plants now. And if you're interested, there's the Gen 4 plants, which are the new kind that they're working towards. Large atoms are split. So uranium is split into two other large atoms, and those are split, and those are split, and you get a chain reaction. And those chain reactions are controlled with rods that kind of determine how much of these collisions can happen during a certain amount of time. There are toxic waste products. The plants that we use this is real nuclear reactions and it makes real nuclear energy. So we are going to be using fission, and it is somewhat more controllable. And like I said, the new Generation 4, they figured out some safety measures that make it very practical. Hopefully this overview helps you understand a little bit about the vocabulary that we're going to be using for nuclear physics. Alrighty, bye-bye.